where we enter the maintenance phase of the building. So kind of cover the whole process. And we've seen, and construction itself is it's super important for the economy. We've seen this number now to the third time, I think, is $10 trillion that are being spent every year. And also the chart you have seen at least once in the beginning, in the introduction, where we see that there's a huge productivity gap. And we in HILTI, we are trying to address this productivity gap with obviously robotics. So you can see here, and here I have to know, obviously not the first company that has a robot on a construction site. This is our drilling robot. We have it deployed worldwide already, and with the robotics, we address exactly these three things: speed, safety, and accuracy. And with speed, it's not only being faster. I mean, that's what we're trying to do, being faster than the humans, but we also, get a lot of predictability, which is currently not the case. Maybe I'm not sure if you know, but 9 out of 10 projects on a construction projects run over budget. I'm pretty sure every one of you knows something where some public, building of a airport or whatever went way over budget. And so with robotics, and this kind of shows how difficult project management is and how unpredictable all these things are. And with robotics, we try to make this a little bit better predictable. Also, safety is a super important issue. With our robots, we kind of reduce the exposure to dust, for example, to the workforce. Also, exposure to vibrations is reduced, and they don't have to work in these large heights anymore. And last but not least, accuracy, where we can really, maintain accuracy, have a much higher accuracy compared to what's possible now, because all the projects it's super common that a construction, a building is, for example, 10 centimeters longer or shorter than it was originally planned. And so one key component for an autonomous robot is obviously the ability to localize within the construction site. And we're now facing the big challenge that we have the requirement of being super accurate on the whole, basically on the whole site. It must be less than 5 millimeters, actually. That's our hard requirement. And that's why we now propose this, or that's why we are working now with leading academia, with Professor Fallon and Professor Scaramuzza, to have this challenge now already for the second time, to really, give an incentive to the academia to push the limits of SLAM, to look into, how can we make it more accurate, to actually, use it in practice at the end of the day. And so I would like to hand over to Professor Fallon to show you more about the technical details of the challenge.
Okay, thank you very much for the introduction, Michael. So I'm Maurice Fallon. I'm an associate professor in Oxford University, and do a lot of work in mapping and navigation with multiple sensors. And we were involved in the challenge last year. We won the academic track of the challenge, and this year we've helped to organize it with Michael and his team in HILTI. So our background is in multi-sensor fusion and navigation, and we've done a lot of work with robots, bringing them to kind of dirty and dusty environments such as mines, with the Animal robot as part of the Cerberus team in the DARPA challenge, and also deploying Spot, as you can see on the right hand side. That was last week in a construction site. And over the last number of years, we kind of concentrated and focused our effort on multi-sensor fusion. So here are 3 different payloads that we developed for LiDAR, vision, IMU, the same kind of sensors basically that are part of the challenge this year. And you can see some of our results there. But switching to focus more specifically on the challenge was focused on positioning and tracking with this device here on the right hand side. It carries the same sensor combination that we've worked with, that HILTI have got good feedback on, a combination of multiple cameras and LiDAR with inertial sensing. So the device is made up of an integrated logging computer, 5 fisheye cameras pointing in different directions, wide field of view for all of those challenges that we were talking about earlier. PTP synchronized IMU, a HESA grade LiDAR, admittedly one with a smaller field of view, which was actually one of the challenges that we were trying to insert into the competition to look for a sweet spot between different sensor fusions. It's actually something that Michael mentioned in his talk. And then again, the PTP synchronized, and then the final detail is this little stake that's on the front of it. There's a if you look at the very front in the center, there's a stake that's pointing onto the ground, and that's core to the positioning system that we developed, or that Michael's team developed for inferring the ground truth down to millimeter accuracy. We had diverse test environments. These are 2 of the 3 test environments. Construction site, Liechtenstein, bare concrete, a lot of unstructured layout at that phase of the construction. We specifically sought out where there were entirely dark environments where the sensors, the vision sensors would fail. And then just by the nature of the way in which we do the operation, sensor occlusion is quite common. And then on the right side, more of a historical facility. This is at Sheldonian Theatre. It's a 400-year-old building in Oxford that has a lot of very narrow winding staircases, small doorways, small passages, again with similar lighting transition challenges. And the approach effectively involved first using a very high-end scanner made by ZMF, a German company, to laboriously build a 3D model. And as if to motivate the need for speed and for safety, is that this took 4 days and required us to close the theatre. And just the logistics of being able to build a 3D model with such slow data acquisition time is almost the motivation for SLAM by itself. But given that prior model, then carrying the device around and positioning it in such a way to infer references. So this is just a little visualization of the site in Oxford. And then this is the 3D point cloud. The 3D point cloud is not used in any way in the challenge, but within that are the position references. So that's the site that's used for half of the challenge. And at this point, I'm going to hand over to Linton, who did most of the heavy lifting on this project, to explain the establishment of the reference points.
Yeah, just some details on how we achieved millimeter accuracy for the ground truth, because people come to ask me, what's going on behind the scene. So what you see here is we use this a high-grade survey LiDAR, which goes up to a range of 300 meters. It's a 360-degree LiDAR, also with camera view around it as well, so that we can use to colorize the point. And then you can see some of these targets we use to place on the floor as well. I'll talk about them in a second. So in here you see a video that when we are surveying the site, besides by moving the LiDAR from one place to another, we also put down these reference points. The tip of the system align with the center and balance it out to have a target sitting on top. And the LiDAR will pick out the center of that target to be able to use the contrast in the intensity from the LiDAR to further align the point cloud. So in the end, we'll have a point cloud that is very accurate. In the meantime, all these reference points would be the ground truth when we are taking our device going around. So here you can see that if I can get the video to play, you can see when we are going on the left, we have normal channels. You probably see my face in some camera multiple times. So we have to carry the data from the ground cover off. So we will place that tip on those markers, and that will know the position in the point cloud, and that's how we achieve accuracy in that. So they are sort of sparse ground truths. And in the future, we also provided some dense ground truths for you to debug your algorithm. Yeah. It's dense ground truths by aligning the individual scan into the file file high quantities. So this is a look on the data set. You can see it here. These are some dark environments. If you couldn't see on the screen, you can see that it is dark. And then we're getting through some of these narrow staircases, as it's seen here. And sometimes we're getting through some doors that is half open, half closed. And also because I'm holding the device in front of me, so purposely to block some of the view to mimic what's going to happen in real construction environment. So this is the list. It was in the challenge already. You can see the numbers go up to probably 21. So we actually have some additional sequence which we can use for in the future, either to be a continuous benchmark for SLAM system, and then these ones will be released as a data set people can use and with some dense ground truth as well. So yeah, so we'll have this the Michael's team on the web. We built this automatic evaluation system. You probably have used it when you submitted your results. So Michael was already mentioned there was 7,000 submissions. Some submitted more than others. This automatic evaluation. These ground truth points are used to evaluate, giving you the score based on your the sort of the ATE values. You'll get different point scores on this. Mars, you want to make it?
Okay, just a few last things. For those who are listening online, I'd imagine it's the majority of people who've been entering. The 3D point cloud that I showed earlier will be made available. It's currently served in that web browser at the moment. We're determining the trajectories of some of the sequences in high frequency by alignment to that scan. And then there's a very long sequence that wound in and out of all of the corridors and staircases of the theater that we'll make available, as well as a data set paper describing the main performance features. Maybe afterwards, or if there's a few minutes for discussion, I'd be interested to hear people's interest in other metrics that might be useful to develop for the construction sector. Vision inertial, so obviously doing away with the main expensive power consumption sensor of LiDAR is another leaderboard that we've had. Global localization, so given an image or given a point cloud, where is it within the entire facility is another problem that can be addressed with this challenge. And with the extra sequences, we may look to address that. There are other challenges that some of the organizers actually have run on semantic segmentation. So within a pipeline of tripod-based scanning or Matterport scanning to extract semantic meaning from doors and walls and furniture and so on. Could you actually do that with data sets like this that are taken in motion? That's one of the use cases. Obviously, surface reconstruction is another challenge. Just a couple of reflections on the results, not going into specific details on the winners. We tried to actually get the challenge to kind of require sensor fusion between LiDAR and vision, but yet again this year we've seen that LiDAR approaches, or predominantly LiDAR approaches, were the best performing ones, even despite having restrictions with the LiDAR. So the loop closure mechanisms that are found with LiDAR still seem to be sufficient for the scale of environments that we're testing here. Vision obviously is intrinsically motivated by the reduced costs and less complexity in actually developing the systems. I think there's a wider challenge on being able to do wide offset visual loop closures. The problem of being able to just use the camera images to know within 1 centimeter where you are if you haven't actually been precisely in that location. So coming across one of the open spaces where there's a strong visual offset, and it's difficult to do visual loop closure in those environments. Those are research problems that would be intrinsically motivated here. And then all of these sensor systems assume and rely on continuous odometry tracking, and construction engineers have a terrible problem of not pointing the sensors where you'd like them to. So putting them either occluding them, or as you go through doorways and tight spaces, blocking them. So I think there's a lot more work to be done on using the inertial sensing as a fallback in that capability. So those are just some references. Actually, I don't think we're going to take questions. We're going to flip back over to Michael to announce the winners. Okay.
Actually, we're gonna move now the part of the best paper award before we're announcing the winners of the challenge.
Oh, okay.
Gino, would you like to? So let's. we'll directly switch to this slide. Okay, so these are the best paper awards. Please go ahead.
Right, so these are the best paper awards for the workshop papers. So for the first place, we have Chana Ross, Yakov Miran, Yuval Goldfrapp, and Dotan Di Castro, and their paper is titled AGPNet, Autonomous Grading Policy Network. So congratulations. Unfortunately, the team is not present here today, but they're here. Well, they're present on Zoom. So I'll accept the certificate on their behalf. So next, for the second place we have Jingyoung Liu, Yu-Ming Zhuang, and Joshua Bart, and their paper is a computational framework for robotic quality assessment and management in construction. So if you can come up and collect the certificate.
There you go.
Thank you so much.
Congratulations.
For the third place, we have Samuel Landgraf and Amy Sniffen, Alberto Quattrini, Lee, and Devin Balcom, and their paper is titled Towards the Autonomous Underwater Construction of Cement Block Structures with Free-Floating Robots. So if you're here, one of the authors, you can come up and collect the certificate. Thank you.
Okay, and thank you all. With that, we continue to the SLAM challenge. Just some statistics about who has participated. We had around 40 teams, which was great for all of us. Last year we had around 20, so we really were able to double the size. And as already mentioned by Maurice, most of actually the top four are LiDAR IMU dominated. And you can see here an example of the accuracy of the winning team. I told you in the beginning, our main use case requires less than 1 centimeter accuracy. So this is kind of where we're aiming at. This is our major requirement. And with these sensors that are off-the-shelf sensors, it's great to see that already 40% of the points that we measured are within that range. So compared to last year, where we are around 10 centimeter accuracy on average, this is really a tremendous improvement. And it really shows what on the algorithm, but also on the hardware side, is improving how fast these things are actually improving. And there's also one more thing that I would like to mention before announcing the winners. So these data sets, they are online and they will stay online. And so we are actually hoping that all of you are using them for testing and improving the algorithms. And we will also keep adding new data sets and new challenges to it. And we're hoping that with your feedback, we're going to make it even better than it is now. So without further ado, these are the winners of the HILTI SLAM challenge. Third place goes to Wai Shu, Cheng Lui, Ko Chang Wang, Xiu Liu, and Fu Sang from Mars Lab. Congratulations. Is anyone from this team here? Okay. Then second place goes to Frank Neuhaus and Till Kosman from Vision Robotics, Germany. Congratulations. I know that both of them are not here, unfortunately, but they're online. So, and then finally, the winner of this SLAM challenge is Milad Ramensi, Kavit Kat, Kasra Kosusi, Fred Pauling, and Payman Mogadam. Congratulations. So we will hear just after these presentations, short presentations from the first and second place, showing how they achieved this really outstanding results. So please stay tuned. Then Maurice also mentioned we're not only having we have a second leaderboard as well that is based on vision only. So we have this separate prize that kind of values the best vision only solution. And this year, this goes to Stefan Leutenegger with his OCFIS 2.0 algorithm. Congratulations, Stefan. Stefan is also online, I think. And then we come to, of course, the most important things for most of the students who participated, the cash prizes. So we stated on the homepage that actually we want to, incentivize students that are working in this field to really, get the cash prizes to continue working, doing their great work. And for that, the first prize with $7,000 goes to Waishu and Waishu and his collaborators. So congratulations for that big prize. Second prize goes to hard to read. Second prize goes actually to Professor Hoyang Wang, who just presented here to his team. Congratulations for the second prize of $3,000. And third prize with $1,000 goes to Jia Chu from Beihang University and the Chinese University of Hong Kong. Also, congratulations. And last but not least, Wei Thang and Sen Wang from TU Munich get the $1,000 for the best vision only solution. Congratulations. And with that, I would like to thank the organizers, everybody who participated, and most importantly, all the participants of the challenge. So thank you all for participating and creating this great challenge.